Chapter 10. Association. Section 1. Primary key. When we talked about the concept of structured data, we said that the fields of the data table have names, but the records have no names. So how do we identify the difference between one record and another? We know that each record corresponds to the information of one thing. Which is it? How to determine that the current referenced or operated record is the one corresponding to the expected thing? It is often unreliable to use the order of a record in the table sequence to identify, because the sequence number will change with the insertion and deletion action. In the examples of the previous chapter, most of the table sequences we created and referenced have a field with values that are unique in the whole table sequence, such as the ID field in the personnel table or the DT field in the stock table. Structured data uses this unique field value to identify a record. In a data table, if there are one or more fields and the values of any two records in this field or the sequences of values in case of multiple fields are different, we can set this field or these fields as the primary key of the data table. Note that the primary key is set manually and not found automatically. There may be multiple fields in a data table that meet the condition of primary key, that is, uniqueness, but we will only select one as the primary key. A primary key must be unique, but a unique field may not be a primary key. The field value of the primary key of a record, also known as the primary key value of the record, is also referred to as the primary key when the context is unambiguous. Because the primary key is unique, that is, the primary key value of a record will not be repeated in the whole data table, the primary key can be used to uniquely identify a record. We say that the current referenced or operated record is a record with a primary key of XXX, so there will only be one such record, and there will be no mistake. For a data table with a primary key already set, in principle, it is not allowed to add new records with the same primary key as existing records. When inserting and deleting records, the primary key will not change. Using the primary key to identify a record is more stable than using the sequence number. However, primary key is not required. A data table without a primary key usually only appends records instead of modifying, deleting existing records or inserting new records in front, because these actions will change the sequence number. In fact, we are not unfamiliar with the concept of primary key in our daily life. All students in the school will have a unique student number. The attribute of student number itself has no effective information, and its function is only to uniquely identify a student. It will not work to directly use students' names. People may often have duplicate names, so it is difficult to accurately identify a student. For things like orders, they don't have a name. They need a unique number to identify them. Otherwise, we don't know how to determine which order we are talking about. Other similar ones include flight number, bank account, telephone number, etc., which all play the role of primary key. The primary key in daily life is almost everywhere. The primary key of structured data is only an embodiment of people's daily experience in the programming language. The primary key is the name of the record. Setting the primary key is to give the record a unique name. SPL provides some functions for primary key. A2 uses the keys function to set the primary key of the table sequence as the ID field, and A3 uses key to calculate the primary key of a record. For the table sequence with primary key set, key icon will be drawn on the primary key field when the values are displayed. However, SPL does not check the uniqueness of the primary key when it is set. Whether the primary key is unique is controlled by the programmers themselves. Using the grouping operation we have learned, it is easy to judge whether a field is unique in the data table. Just see if the sequence after distinct is as long as the original table sequence. When inserting records, SPL does not check the uniqueness of the primary key. This code will not report an error. SPL only checks the uniqueness of the primary key when it is required. This has the advantage of better computing performance, and each check is a time-consuming action, but the disadvantage is that there may be potential errors. The principle of SPL fully believes in programmers and leaves freedom to programmers. The main usage of the primary key is to identify records, that is, to find a record with the primary key value. SPL uses the find function to return the record whose primary key is its parameter. If it cannot be found, it will return null. In the table sequence we are using now as an example, the primary key of records is arranged from small to large just like the sequence number. This is to facilitate the generation of a unique field. However, SPL does not have this requirement for the primary key. It can be out of order. A4 can also normally find the record with the parameter as primary key. Since SPL does not check the uniqueness of the primary key, if there are records with the same primary key in the table sequence, the find function will not report an error. It will find the first record and return, which is a bit like select at 1. By the way, the find function is similar to position function. It is not a loop function. Its parameter will be calculated first when being called, and there will be no tilde, hash and so on. It is a common action to use the primary key to find a record. If the table sequence is relatively large, the search speed will be slow, because this search usually needs to compare one by one. SPL provides a mechanism to index the primary key, and the search speed will be much faster. The index function will create an index for the table sequence with a primary key, and the index will be automatically used by find after the index is created. When you execute this code and compare the running time before and after indexing, you will find that the performance gap is very large, but it also needs to be executed 10,000 times and use interval at ms to capture. After the index is provided, the method of comparison one by one is no longer used. The specific method is far beyond the content of this book, which will not be explained here. SPL requires the uniqueness of the primary key when creating an index. When index is executed, SPL checks whether the primary key is unique. If it is found that the primary key is not unique at this time, an error message of duplicate primary keys will be reported. SPL seems a little lazy and won't take the initiative to do things until necessary. Unlike the operations mentioned earlier, primary key and index can only be created for a table sequence, not for a record sequence. They are part of the data structure. However, find can be used in a record sequence, only that it can't use the index. It can only compare one by one. As an aside, if the primary keys are in order, find also supports a fast search technology called binary search, which is much faster than comparison one by one. It is close to the index, but still can't catch up. It can be used for a record sequence without index or a table sequence that has not created an index. The select function and pose function also support this binary search. Interested readers can refer to the relevant documents of SPL, because high-performance computing is not the focus of this book, we won't elaborate here. Let's review the grouping operation mentioned in the previous chapter. Observing the table sequence returned by groups, it is obvious that the field corresponding to the grouping key value is unique, that is, this field can naturally constitute the primary key of the table sequence returned by groups. Therefore, the field value used for grouping is called key. Careful readers may have found that when viewing the returned result of groups, the small key icon has been drawn on the grouping key. Section 2. Foreign key. With a primary key, we can uniquely identify a record. Then, we can establish the association between the records of different data tables. First, generate two tables with primary key for experiments. For simplicity, we use integers as primary key. A2 is a department table, each record corresponds to a department, the DID field is the department number, which is used as the primary key, and the name field is the department name. A3 is the employee table, each record corresponds to an employee, each field is the employee number, which is used as the primary key, and the nation field is the employee's nationality. The employee table usually has a name field, but it's useless here, so we won't generate it. The key points are the depth field of A3 and the manager field of A2. Depth stores an integer representing the department to which the employee belongs. The department of the employee corresponding to record E in the employee table is the department corresponding to record D, with E.depth as the primary key in the department table. We will also say that record E is associated with record D. The manager field of A2 indicates the manager of the department. The manager is also an employee and will also appear in the employee table. The manager of the department corresponding to record D in the department table is the employee corresponding to record E with D.manager as the primary key in the employee table. We also say that the two records D and E are associated. Understanding this relationship makes the role of A4 clear. Because the randomly generated data cannot guarantee that the manager's department is his own department, it should be adjusted in A4 so that this data can be used. Now we want to list all the people in the RD department. This is a simple selection problem, and we should use the select function. However, there is no department name in the employee table, and there is only the department number. The selection can only be done by using the number to find the department name in the department table. Similarly, we can also list all departments where the manager is American. In this way, we associate the employee table with the department table and can jointly use the information of the two tables for operation. The depth field in the employee table is always the primary key of a record in the department table, and it is also used to represent this record in the department table. We call this field a foreign key, and a more complete saying is the foreign key pointing to the department table in the employee table. Through the foreign key, we can refer to some fields of the associated record in another table in the operation of a table, and the two tables are associated by the foreign key. Similarly, the manager field in the department table is also a foreign key pointing to the employee table. The primary key may consist of multiple fields. Correspondingly, a foreign key may also have multiple fields, but it is relatively uncommon, and we won't give an example here. When there is a foreign key relationship between two tables, for example, a field in table A is a foreign key pointing to table B. We also need to know two terms. Table B is the dimension table of table A, and table A is called the fact table. The relationship between the dimension table and the fact table is relative. When we care about the foreign key depth of the employee table, the department table is the dimension table of the employee table, while when we care about the foreign key manager of the department table, the employee table is the dimension table of the department table. Dimension table and fact table are often used by programmers when discussing database operations. We don't use this kind of technical vocabulary in daily data processing, but it's better to know. In the terminology of database, it is also said that foreign key association is many-to-one association, that is, multiple fact table records may be associated with the same dimension table record. Foreign key is not an unfamiliar concept. Dimension table is the code table we often use. We list some frequently referenced attributes of things in a code table and give a code, i.e., primary key, to identify them. When referencing, we only use this code, i.e., foreign key. For more detailed information, we use this code to query the code table. For example, the owner's name, address, and other information will be listed with the phone number, while there is only the phone number in the call record. The phone number is the primary key of the phone book. The phone number in the call record is the foreign key pointing to the phone book. The phone book is the dimension table of call record, and call record is the fact table. In the calculations of call records, it is often possible to use information related to phone numbers, such as querying the number of calls made in Beijing, which uses foreign keys to find the fields of associated records. There are also others, such as bank accounts and bank transaction records, commodity information, and trading records. It is very common to use dimension table information in the operations of fact table. Why don't we directly copy the dimension table fields to the fact table? Readers who have experience with this code table will know the answer. There are many information contents in the dimension table. If they are copied into the fact table will be very large and occupy a lot of storage space, resulting in low performance. Moreover, the dimension table is likely to change, such as department name and owner's address. If they are copied into the fact table, once they change, the fact table will be updated, and the fact table is usually much larger, and it is very troublesome and inefficient. If it is an independent dimension table, you can always get the latest information by modifying the dimension table and temporarily fetching the dimension table fields during the operation of the fact table. Having understood the concept, let's continue. Now list the employee ID and the department name into a table. This is very similar to the VLOOKUP function in Excel. That's how the code table is used. However, it is obviously very troublesome to always use find to write, and the efficiency is very poor to calculate every time. For example, if we want to list the ID of the manager of the employees department, we have to write this find twice. This is more like VLOOKUP. Excel has to write VLOOKUP twice to reference two columns of the associated table. SPL obviously won't fail to take this problem into consideration. This kind of routine operation for structured data can't be so troublesome. SPL provides the switch function to realize the association operation of foreign key. The switch function will switch the foreign key field to the corresponding dimension table record. The A5 code is equivalent to executing A3.runDept equals A2.findDept. Before executing A5, look at the value of A3. The dept field is an integer. After execution, look at A3. The dept field still looks like an integer, but it changes color and is displayed on the left. Double-click the value of a dept, and the result may appear in the value display area. The value of dept field has become a record. Double-clicking it will display the details of this record. The just displayed value with changed color is actually the primary key of this record. Since it is a record, of course, its fields can be referenced, and dept.name and dept.manager in A6 can be calculated normally. The function name switch is used because it can also switch the field valued as a record back. A5 switches the foreign key to the record of the dimension table, and A6 can use it to reference the field of the dimension table record. A7 switches the field now valued as the record back, and is equivalent to executing A3.runDept equals dept.key. However, switching back is rare. After being processed by switch, it seems that the records of the two tables are really connected. The field value of this table is the record of another table. You can reference the fields of another table through this field. This is much more convenient than VLOOKUP. Accordingly, the manager field in the department table is also a foreign key and can also be switched to the record in the personnel table. For example, we want to count how many American employees have a Chinese manager. Foreign key relationships may have multiple layers. In this case, it will be difficult to describe if we still use the find method. If you are interested, you can also try to think about how to use VLOOKUP to realize this multi-layer association in Excel. For the foreign key switched by the switch function, the point operator can be vividly interpreted as '(s). The dept.manager.nation in A6 can be interpreted as the department's manager's nationality of the current employee. You will not find it difficult even if there are many levels. Such a syntax is simple to write and easy to understand. Generally, the value of the foreign key field must be within the range of the primary key value of the dimension table, but sometimes it may exceed the range. For example, before the department of a new employee is determined, the dept field is filled with 0, and there is no corresponding record in the department table. In the code B4 for generating data, we deliberately find some employee's dept and fill it in as 0, and then we can observe the calculation results of the 3A5. Note that it should be executed separately, not sequentially, because A3 will be changed after execution, and it is meaningless to continue to execute another A5. When the switch function cannot find the dimension table record corresponding to the foreign key, it will fill in the foreign key as null, and the subsequent reference of its field will not report an error, but will return null, and the corresponding B5 will not be 0. The @I option will delete the fact table records that cannot find the record corresponding to the foreign key, ensuring that all the foreign keys of the fact table records after switch are correctly switched to dimension table records, and the corresponding B5 will return 0. While the @D option only retains the fact table records that cannot find the corresponding record of the foreign key, and cannot perform the foreign key switch, and the corresponding B5 will report an error. Using foreign key to associate two data tables is often used to temporarily concatenate some fields of the dimension table to the fact table. That is what VLOOKUP does. In most cases, it is not intended to change the field of the fact table. Although the switch function is convenient for association operation, it will change the foreign key field value of the original fact table. If we only want to append dimension table fields, we need to do another step of switching the foreign key that has become a record back to the foreign key, which is troublesome. Moreover, if we encounter the situation that there is no correspondence that we just mentioned, the foreign key will be filled in as null, and the information has been lost and cannot be switched back. SPL provides the join function to achieve this goal. A5 will add depth name and manager fields on the basis of table sequence A3, and fill in the employee's department name and manager ID respectively. The depth field will remain the same. If the corresponding dimension table record cannot be found, the newly added fields will be filled with null. The join function will generate a new table sequence, and the original A3 will not change. The join function can also support multi-field primary keys and foreign keys. Because they are not common, we won't give examples here. When you need to use them, you can consult the relevant SPL documents and understand the necessity of multi-layer parameters. The switch function does not support a dimension table with multi-field primary keys. It can only switch single-field foreign key. It is very common to use a foreign key to find the corresponding record in the dimension table to reference some fields of the associated record. However, the business is complex. Sometimes the associated records cannot be determined simply by a foreign key, but need a condition related to the interval. Go back to the personnel table often used in the previous chapter and create a BMI comparison table. Now we want to add a field to the personnel table A2 with BMI information to list everyone's weight type. If the BMI comparison table A3 is used as a dimension table, it has low and high fields to represent the BMI interval of a weight type, but does not have a field suitable for primary key. It also appears that there is no field in personnel table A2 that can act as a foreign key. However, it is obvious that there is an association between A2 and A4, and each record of A2 will correspond to a record of A4. Interval association is also a common association. How should it be implemented? We can of course simply use the select function, just like using find function at the beginning of this section. Here, we need to judge whether high is null, and low does not need to be judged, because SPL stipulates that null is the smallest, and null less than or equal to BMI will always get true. In fact, interval association can also be understood as foreign key association. If we modify the BMI comparison table and add the BMI segment number calculated by pseg function to the personnel table, we can see the foreign key relationship. The modified BMI comparison table A3 has a primary key and can be used as a dimension table. The BMI type field added in A5 is the foreign key pointing to A3. We can also use switch function to establish association. Interval association is also a foreign key association in essence. It's really troublesome to create a foreign key for the personnel table. Actually, we wrote the code as above to help you understand that the concept of foreign key can be extended to this situation. In fact, we can directly spell the target field with pseg function. Generally, interval association process does not generate a foreign key, but the concept of dimension table and fact table can still be used. If, like this example, only the type field needs to be referenced, we will not even generate the comparison table, but directly use the sequence and pseg to calculate and reference. Like all foreign key associations, interval association is also many-to-one relationship. Even if the dimension table is not generated, this association relationship still exists logically. Section 3. Merge. If there are two Excel files, such as the order table mentioned before, they may be made by two persons respectively, and there may be some duplicate records. We need to pick out these duplicate records and merge them into a table without duplicate records. Originally, this is a very simple task of set union. We have learned set operations and can directly use operators such as intersection and difference. However, we also know that different records in the table sequence will never be equal, and the records in different table sequences will never be equal. Of course, the table sequences read from Excel files are different table sequences. In this case, they are not suitable for set operations. SPL provides merge operation function to complete this task. Quite simply, the merge function compares the contents of the records. The ETU option indicates to get the union. Without this option, it will directly concatenate the two table sequences, that is, to get the concatenation. We'll talk about it later. Similarly, the merge function can also get the intersection, that is, to get the duplicate records, just replace ETU with ETI. The merge function will compare all fields of the whole record. If any field is different, it will be considered that the two records are different. Such comparisons are time-consuming and sometimes unnecessary. For example, for this order problem, we believe that the producer is conscientious and responsible. As long as the order number is correct, the order content will not be wrong. However, there may be duplication and omission in the order collection process, resulting in duplicate order numbers in the two files. And we only need to pick out the records of duplicate order numbers. By adding a parameter to the merge function, we can make it compare only this field. Or for records with primary key set, the merge function will only compare the primary key. The operation is same for intersection, just replace @u with @i. If the situation is more complicated, both producers may make mistakes. We need to see if the records with the same order number in the two files have different contents. Therefore, we need to select the records with the same order number and compare the whole contents to see if they are the same. A2 will calculate those records in A1 with duplicate order numbers as B1, but retain the record sequence composed of A1 records. Correspondingly, B2 will retain the records in B1 that duplicate the order number of A1. A2 and B2 are both the intersection of A1 and B1, but they are only the intersection in the sense of comparing the order number, and the whole contents are not necessarily the same. Then use merge @d in A3 to calculate the full content difference set between A2 and B2, so that we can get the records in A2 that have different content with that of the corresponding orders in B2, and get the order numbers of these orders in B3, that is, the orders to be reviewed. This complexity occurs when set operations involve structured data. The same primary key, or a relatively critical field, does not mean that the whole record is the same. When we need to judge that the records are the same when doing intersection, union, or difference, we may use only the primary key or the whole record. If only the primary key is used, the exchange law will not be satisfied. This is not only that the order of members may be different, but also the content may be totally different. Pay special attention when writing code. Now let's talk about this @o option. By default, the merge function assumes that the data is ordered, for example, from small to large, thus the comparison speed is very fast, and no sorting is needed. The @o option tells the merge function that the data is out of order and needs to be sorted first. In our current example, the orders are arranged in order according to the order number. It doesn't matter if @o is not written. Another note is that the merge function is preceded by a sequence such as sequence A1, B1, which can calculate the union or intersection results of multiple record sequences at the same time. However, it is relatively uncommon, and we won't give examples here. The merge function is also valid for sequences, but single-valued sequences generally use the set operator directly, and rarely use the merge function. Section 4. Join. Let's continue to see the above order example. After picking out the records with the same order number but different contents in the two files, we want to spell the fields except the order number together and compare them. That is to form a data table with twice the number of fields, except the order number. We usually use the join function to accomplish this task. The join function of A3 returns a table sequence with two fields, A and B respectively. It will concatenate the records in A2 and B2 according to the ID field value, that is, fill the A2 record and B2 record with the same ID into field A and field B respectively as a record in the return table sequence. The value of field A or field B is also a record, which is a bit like the result of a foreign key being switched. After we understand the calculation result of A3, although A4 is long, it is easy to understand. Unlike merge function, the task of join function is often to make the data table wider, and merge @u will make the data table longer, that is, more records. A bigger difference from merge is that the data tables targeted by merge are generally of the same data structure. While the common scenario of join is two or more data tables with different data structures. Let's continue to use the personnel table generated earlier. We now have a personnel table with gender, height and weight, as well as an employee table with nationality and department. We want to make the two tables into a wider table. If the name field of the personnel table is the same as the ID field of the employee table, it means that it is the same person. Let's sort out the code used to generate data. We don't use the department table at the moment, just discard it. the ED in employee table A2 is disordered. Let's finish the task. Because the name of A3 is a string type, which is different from the ED of A2, it needs to be converted and written as int name. We can also convert A2 and write A4 like this. This is the calculation result of A4. A table sequence with two fields. The field values are A3 record and A2 record respectively. Because we did not set the primary key for A2 and A3, the development environment will display the fields of the record as a sequence. It can be seen that the first field of the records on the left and right sides of the same line, that is, name and ED, are the same. This is the result of the join operation. It will spell together the records with the same name in A3 and ED in A2. Then A5 can easily get the desired results, which will not be explained in detail. Two data tables can generate a data table with two fields through the equal relationship between certain fields, or expressions. Based on this new data table, the fields of two original data tables can be referenced for operation at the same time, so as to complete the association of the two tables. The field, or expression, used to determine association is called association key, and records with equal association key values are called associated records. This association operation is called join. The foreign key association mentioned in the previous section is also a join operation. It uses the foreign key of the fact table and the primary key of the dimension table as the association key. However, we rarely express the operation result of foreign key association as a table sequence using two fields with records as values as a data structure. Instead, we are used to using the previous method to switch the foreign key with the switch function or spell the dimension table fields into the fact table with join, not the join we are talking about. If we already set the primary key for A2 and A3 tables, we do not need to write the association key during join. We need to change the generation statement in A3 to directly use integers as the values of the name field, so that the primary keys of the two tables do not need a conversion and directly serve as the association key. The join using the primary key as the association key is called the homo-dimension association, and the two tables are also called the homo-dimension table to each other. In database terminology, the homo-dimension association is a one-to-one association. That is, a record in an association table will only be associated with one record in another association table, not multiple, because the primary key is unique. Let's continue with this code and change it a little bit. A2 randomly selects 80 integers between 1 and 100 as the primary key to generate 80 records. A3 directly selects 1 to 90 as the primary key to generate 90 records. In this way, the primary keys of A2 and A3 still have a lot in common, but they also have a small number of primary key values that the other does not have. Because of random generation, the result of each running may be different, but it does not affect our discussion. Look at the result of A4. The left and right are still equal, but there are obviously missing sequence numbers, that is, primary key. Looking at A5, of course, it will not be 100, but it is not 80 or 90, but smaller. The join function will find records with equal association keys in both tables to associate. If the association key value of one table does not exist in the other table, the corresponding record of this table will also be discarded. This join is called inner join. The association key set in the result of the calculated table sequence is the intersection of the association key sets of the two associated table sequences, that is, B5 in the above code, and A5 is bound to be equal to C5, which is usually less than the length of A2 or A3. Let's try again after changing the last two lines of code. Execute again, and then look at A4. The record primary key in the values of the P field is complete, ranging from 1 to 90, and corresponds to the records of A3 1 by 1. Some records of the E field are filled with null. A5 is also 90, the same length as A3. The join with @1 will be based on the association table on the left. If there are records with the same association key as the left in the right table, it will be associated. If there is no record, it will be filled with null. The association key value of the result table sequence is the same as that of the left table, and its length is also the same as that of the left table. This join based on the left is called left join. Some database systems also have right join, that is, join based on the right. However, SPL does not provide it. It is not necessary because it can be done by swapping the parameter position. And this at 1 is the number 1, not the letter L. It means that the join is based on the first parameter. Continue, then look at A4, because the primary key of A3 is from 1 to 90, the records in the front exist. Pull the table to the end, and the last few records can be seen. Now there are null field values on the left and right sides, and A5 is greater than 90, but it is often not 100. The join with at F will consider both tables. If the association key value exists in either side, a record will be generated in the result table sequence. If both sides have records with association key value, the records will be filled in the corresponding field to realize association. For an association key value, if only one table has a corresponding record, fill it in the corresponding field and fill null in the corresponding field of another table. Finally, the associated key value set in the result table sequence will be the union of the associated key sets of the two table sequences involved in the association, or B5 in the code, and A5 will be the same as C5, usually greater than the length of A2 or A3. This two-sided join is called full join. Inner join, left join, and full join are very important concepts. When performing join operation, we must make sure which kind of join to use. The results of different joins will be very different. Foreign key association is usually left join, that is, based on the fact table. If the switch function cannot find the associated record in the dimension table, it will fill the foreign key field with null. While switch at I is equivalent to inner join. When the associated record cannot be found, the relevant record of the fact table will also be filtered out. Join and join at F are a little similar to merge at I and merge at U. In fact, join operation can be used to realize the intersection and union of two table sequences according to the primary key. A piece of data may have multiple production sources, and then spliced into complete data. It may be divided into multiple parts by row, which will be combined with merge function, and the duplicated parts will be processed in the process. It may also be divided into multiple parts by column, and join function is used to combine them. These data also need to be concatenated reasonably without dislocation. Let's look at another association case. Based on the employee table, a 12-month salary table is generated for everyone. A3 needs two fields as the primary key to ensure uniqueness. Now we want to calculate the total income of each department. The department information is in the employee table, while the income information is in the salary table, and this task requires the association of the two tables. Using the foreign key association we have learned, the employee table is regarded as the dimension table of the salary table, and we can solve the problem. There is no problem with this code. However, we can also use join to deal with this association that uses a part of the primary key as a foreign key. The same correct result is calculated as just now. Look at A4. The result is like this: A2 records are repeated in E field. Each A3 record is associated with an A2 record, while each A2 record is associated with 12 A3 records. The length of A4 is the same as that of A3. This association, which uses part of the primary key fields as a foreign key, is also called primary subassociation. The table with fewer primary key fields is called primary table, and the table with more primary key fields is called subtable. A primary subassociation is a one-to-many association, which is the opposite of a foreign key association. From the standpoint of the subtable to look at the primary table, it is a foreign key relationship, while from the standpoint of the primary table to look at the subtable, it is a primary subassociation. We will also use this join to handle the primary subassociation, instead of always using switch and the join mentioned in the previous section. Sometimes, we'll do a groups to the subtable first and then join with the primary table. For example, for the previous problem, after A4 performs group aggregation, a table sequence with grouping key as the primary key is formed, which has the one-to-one homo-dimension relationship with A2. Theoretically, in foreign key association, we can also perform a groups to the fact table using the foreign key as a grouping key to form a table that has the homo-dimension relationship with the dimension table, but we usually don't do that, because a fact table often has multiple foreign keys. If we perform a groups according to a foreign key, other foreign keys can't be processed. In most cases, the subtable will only have one primary table, so it is no problem to perform a groups according to the association key and then do a homo-dimension association with the primary table. Of course, in foreign key association, we can also directly perform join operation just like in primary subassociation, and put together the records of the dimension table and fact table. One dimension table record may be associated with multiple fact table records. In fact, the join function mentioned in the foreign key section is doing this, but it also does the action of referencing the dimension table field after association, because this combination action is more common. The length of the result table sequence is also the same as that of the fact table, so the function is also named join. Now we have encountered several join modes, one-to-one, one-to-many and many-to-one. Is there a many-to-many mode? There is almost no business meaningful many-to-many join in structured data operations. Many-to-many join only exists in theoretical analysis or mathematical operations. There are basically no associations unrelated to the primary key in daily data processing, so we don't have to pay attention to them. SPL provides the XJoin function to handle join of any conditions, and can also realize many-to-many. But we can only give a mathematical example to illustrate it. XJoin will calculate the Cartesian set of the sets involved in the association. Note that we say set instead of table sequence, because it is too difficult to find reasonable business examples for structured data. The process can filter the Cartesian product under specified conditions. For the concept of Cartesian set, unfamiliar readers can search on the internet. Let's give a simple example to understand it. It is not difficult to understand the calculation results of A2, B2, and C2. Take a member from each set to form a record, and all possible combinations are included, which is Cartesian product. It can also be understood as a multi-layer loop, and each layer loops through a set. In the innermost loop, the loop variables of each layer are collected to form a record. The set of these records is the result table sequence, and its length is the product of the lengths of the sets involved in the calculation. In fact, all the associations we mentioned earlier can be defined as follows. Take a subset that meets a certain condition from the Cartesian product of the data tables participating in the association. All the join operations we have learned can use the condition of equal association key value, and SQL defines the join operation in this way. This definition is very simple, but it does not reflect the associated characteristics between data, which is not helpful to simplify syntax or improve performance. SPL does not adopt this definition, but describes the common association modes separately. You can use different operation methods in different scenarios. Let's use XJoin to realize the generation of permutations previously realized by recursive program. A3 will calculate the permutations of all three members from 1, 2, 3, 4, 5. XJoin first calculates the Cartesian product of 3, 2, 5, and then filters out those with duplicate members id.len not equal to len, and gets a reasonable permutation. A1 and B1 can be changed to obtain the permutations of other values. This code looks much simpler than recursion, but the amount of computation is much larger. We can only try it with smaller values. We spent 3 chapters on structured data and its operations. These contents have far exceeded the query and calculation ability of SQL, that is, relational database. Only recursive association in the most common operations has been abandoned because of its difficulty and less application. In other words, having learned these contents and being able to combine them flexibly, you'll have a stronger ability to handle structured data than professional database programmers who can only use SQL. Combining with Excel and other tabular software to achieve beautiful presentation, you can easily solve almost all the problems of daily data processing.